So if you're asked to determine an empirical formula on a test, quiz, or homework, how do you do that? Well, it's really not too hard if you just follow these steps. The first thing that you're going to need to do is it's going to give you some information about several different kinds of elements, and you need to determine the number of moles of each element using N equals G over W. So it's going to have to give you the grams, and you use the molar masses off the table. Now, sometimes it won't give you mass. It'll instead give you mass percent instead of grams. And if that happens, you can just change the percentages to grams because it's a ratio. It doesn't really matter how much you have. So if you know the percentage, for example, if you know it's 60% one thing and 40% the other, we're trying to find the mole ratio. A formula shows us the ratio of different things in it. So we don't really, we should get the same answer no matter how much we start with. So we can choose any numbers as long as they are in the same proportions. So think about it. Water. If you find the empirical formula of water, you should get H2O, whether you use a cup or a million gallons. It should always be the same ratio. So if it gives you percents, just change the percents to grams. That's what it boils down to. Once you have grams, either from percents or just from grams, you just use the numbers it gives you. You're going to divide each by W and get moles, like we said. Then once you have the moles for each element, you will divide each of those moles by the smallest of them. And what this will do is it will give you relative ratios of the different kinds of moles. And so we do that. And then when you do that, the number you get for each element is the element subscript in the formula. And that's pretty much all there is to it, with one little exception. If you get any answers that are not an integer, every ratio in a formula has to be integers. You can't have 3.5. And we don't want to round off a 3.5 to call it a 4. We don't round these numbers. These numbers that you get in number 3, you don't round them. If it's not a, you round them if they're very, very close, but you wouldn't round something like 3.5 and call it 4. So what do you do if they come out like this? Well, let's do an example. If you came out with 1, if you had a ratio of 3 elements of 1 to 2.33 to 4, we would not write, subscript 1, subscript 2.33, and subscript 4. We would need to somehow fix that. And you wouldn't just round this down to 2. What we'd want to do is we'd ask ourselves, what can we multiply that number by to get a whole number? And the answer is, well, doubling it doesn't work, but tripling it does. Tripling it would get you to 6.99, which is basically 7. So if we triple that, we'd have 7. But since, again, we're comparing the amounts of the different things, we can't just triple that. We've got to triple all of them. So 1 times 3 is 3, 2.33 times 3 is 7, and 4 times 3 is 12. And this here, 3, 7, and 12 would be our subscripts that we would write for that empirical formula. So what are we talking about? How would you do this? Let's actually plug in a real example and see if it makes more sense. So find the empirical formula of a compound. And we're going to give you the mass percent of the composition is 29.1% sodium, 40.6% sulfur, and 30.3% oxygen. So how do we do this? Well, we follow the steps. The first step, if we go back, was, if you wrote those down, is to find the moles of each. So using these percents, like we said, a percent is just going to be the same thing as grams. We can use those for grams in these problems, so we just write grams, write grams, write grams. So those are our G's. We're going to divide them each by W. So 29.1 divided by sodium's molar mass is 23.0 if we go to 1 decimal place, and sulfur is 40.6 divided by its molar mass is 32.06, which we'll round to 32.1, and oxygen is 30.3 divided by 16.0. That's its molar mass. These numbers coming off of the periodic table, and the top numbers are given in the problem. So now we go through and we divide those. 29.1 divided by 23 is 1.265, and it does not work. Don't round these. Don't round moles. You can, when you're comparing things, when you're finding ratios here, don't round them at all. We got 1.265 to, you can keep going if you like. That's probably far enough, but don't round. Don't call that 1. Certainly don't call it 1.3. That could really mess up your ratios later. So going on to the next guy, 40.6 divided by 32.1. It's 1.265 or 0.26479 797, that's probably good enough. And then this last number, the oxygen number, 30.3 divided by 16 is 1.89375. And so these then are our moles. We just found the moles of sodium, we found the moles of sulfur, and we found the moles of oxygen. We found small n for each of those. So the next thing that we're asked to do is divide each by the smallest. So the smallest, if we look, it's close. These two are very close, but it looks like the sulfur number is the smallest. So when we divide sulfur by sulfur's moles, we get, of course, 1, because it's the same number. And 1.2625, 2 divided by 1.264797. When I get 0.998. 0.998. Now that, I said not to round unless they were close. Well, that is very close. That is very close to 1, so we'll just call that 1. And then over here, this other number, 1.89375, if we divide that by 1.264797, we get 1.49727, blah, blah, blah. Now, if you look at that, that's clearly not close to 1, and it's not close to 2 either. So that's a case of something we're going to have to double or triple or quadruple or something to get a whole number. So, fairly obvious here, that's about 1.5. If we double 1.5, we get 3. So our number there is 3, but we doubled it, so we got to double this, and we got to double this. So those numbers then, 2, 2, and 3, are the subscripts in the answer to the empirical formula. So the sodium gets a subscript of 2, sulfur gets a subscript of 2, and oxygen gets a subscript of 1 for an answer of Na2S2O3. And that is sodium thiosulfate. Thiosulfate. That is our answer, Na2S2O3.